organizers for the invitation. So I'm going to be talking today about some joint work with Anthony Genevois. Which is, so it's one of the last few talks, and for the bravest of you, it's talk number 28. So it's going to be a rather gentle and geometric promenade in the realm of graph products. So graph products have been introduced earlier this week, for instance, in the talk of Anthony, but that was 17 talks ago. So I'm just going to give the basics again. So what do we mean by graph products? So you start with a finite simplicial graph, and for every vertex you choose a group GV, and you define the graph product, which I'm simply going to denote G in this talk, which is obtained from all the GV when you require that two adjacent groups commute. That is, you take the free product and you kill all the commutators of the form G prime if G is in GV, G prime is in GV prime, and V prime are vertices connected by an edge of gamma. So we've seen, nope, bad idea. We've seen some examples already. So if gamma is discrete, so you add no relations, so you get a free product which is just a graph product which is just the free product of all the GV. If now gamma is complete, then you add all the commuting relations. So the graph product that you get is the direct product of all the GV. So that's for conditions on the graph gamma. Now, if you require conditions on the groups themselves, then you get well-known families. For instance, if for every V, GV is taken to be just the infinite cyclic group, then we obtain rags. And if we take for every V, GV is cyclic group of order 2, then we get right angle Coxeter groups. And so for various graph gamma, you interpolate between free product and direct products, and you're allowed to take any local group GV that you want. And the main problem I'm interested in today is for such a graph product to understand its automorphism group. So when I say understand, it can be understanding the structure, for instance, getting a complete description of the automorphism group, and understanding the geometry, etc. So there are some results which are known for that. For instance, in maybe the most studied case of the case of rags. So for rags, so we've got a complete description of the automorphism group, in particular by work of Servatius and Lawrence. We get a finite generating set, and the geometry of rags is also very well studied. Maybe some other result, which is due to Charney, Rain, Stambo, and Vijayan, who studied the automorphism groups of graph products where the GV are cyclic. can be Z, Z mod to Z, or other ones. But apart from that type of results, we don't really understand the structure of the automorphism group of graph products. So in those cases, there are strong restrictions on the local groups. It's either Z or a cyclic group. But what we'll see today is that it's possible to get some good understanding of the automorphism group if we relax all the conditions on the group. The local groups can be whatever, but we put strong condition on the graph. So the result we would like to have is for graphs of large girth, but today I'm going to talk about the case where gamma is a long cycle. And long is generally going to mean n at least 9. So on a cycle on at least 9 vertices. Okay, so we just the class of like right angle Artin groups along cycles give interesting groups, but here we're going to be able to put any local groups on this cycle. So the strategy to understand the automorphism group will be to construct some very nice action, since we like to understand group from a geometric viewpoint, but some sort of analog of the curve complex. And what do I mean by that? We want an action of the graph product on some complex y with a nice geometry, but an action which is in a sense rigid in that not only the group is going to act on y, but actually the automorphism group as well is going to act on y. And we want then to use this action of the automorphism group on this complex to understand the automorphism group, whether from the algebraic viewpoint or from the geometric viewpoint. So the first thing we want to understand is nice actions of graph products on good spaces, and there are some very nice actions. So I'm gonna recall some construction due to Davis. So the Davis complex of a graph product, which is a construction that generalizes the Davis complex that you may be familiar with in the case of Coxeter groups. So we're going to start. We're going to construct a complex as follows. So vertices are going to be in bijective correspondence with the cosets of subgroups of the form G of gamma prime. So I need some notation. Where G of gamma prime for a subgraph, full subgraph gamma prime of gamma is the subgroup generated by the elements, the vertices of gamma prime. So seen as a subgroup of G, and we want to take only the cosets that correspond to a full subgraph, which is a clique. So in the case of Coxeter groups, those are called spherical subgroups. So these are the vertices. We're going to put also edges, and actually oriented edges, of the following form. Take two cosets, G gamma second, G gamma prime. And we're going to put an oriented edge from this coset to this coset if gamma prime prime is contained in gamma prime, and they only differ, and they're also clique, and they only differ by one element. So that gives a graph, and now we take we construct a complex by filling. We fill the cubes in this graph. That is, whenever you see the one skeleton of a K cube, you add this K cube in that complex, and that gives you a complex which turns out to be a cat0 cube complex. That's a result of Davis, and there's a very nice, since it's built by Coxeter, there's a very nice action of the group on the left. So it's a cat0 cube complex. It also turns out to have the structure of a right angle building, but we're not going to use this structure in this talk. So we've got a first action. So let's try to describe what we get for gamma. So a cycle. So the vertices, so the spherical subgroups can happen only if gamma prime is either the empty subgraph, consists of one vertex, or so one vertex here, or two vertices. But you cannot get more than two vertices, because then after that you no longer have a clique. So we've got three types of spherical subgroups. Subgroups corresponding to the empty subgraph, the choice of one vertex or two consecutive vertices. And so I'm just gonna I'm just gonna order cyclically the vertex v1, v2, v3. So these are the possible subgroups. So what do I get? If I do, for instance, the case, the cosets, so I get one time this cosets, which is going to be linked by an edge to, for instance, 1 times GVI. Here I'm going to get 1 times GVI plus 1. But here I also have 1 times GVI VI plus 1. And I also have the inclusions here. And I can start again. Here I'm going to get 1 time G VI plus 1, VI plus 2, 1 GVI plus 2, etc. So if I keep going like that, what am I seeing? What am I actually seeing? So, and that's just for the coset corresponding to the identity element. But then there are all these cosets that correspond to the all the group elements of the graph product. So why do I see appearing? If I see actually I see the cubical subdivision of an n-gon, etc. So actually the complex, the Davis complex in that case, is the cubical subdivision of an n-gonal complex. That is a complex obtained from n-gons by gluing edges together. And so it's an action for which we understand the action pretty well. So the stabilizers for the action are very easy to describe because of the nature of the vertices and edges. So the stabilizers, maybe I should give that a name, X. The stabilizers of vertices for this polygonal complex. For the rest of the talk, basically, I'm not going to look at this complex as a cat0 cube complex, or in that case as a cat0 square complex, but as a polygonal complex. So I'm kind of forgetting the cubical structure, and I'm just remembering the polygonal yellow structure here. So when I speak of vertices, I really mean the yellow vertices for this polygonal structure. So the stabilizers of vertices are going to be up to conjugation spherical subgroups of the form GVI, VI plus 1. Stabilizers of edges are going to be up to conjugation of the form GVI, and polygons have trivial trivial stabilizers. And on top of that, we can see as well that there's it's very easy to understand the quotient. Actually, the graph product acts on this polygonal complex with a single polygon as a fundamental domain. And that fundamental domain is also strict in the sense that there's no identification made here. The quotient of that Davies complex by the action of the group is exactly one polygon. So we've got strict fundamental domain being a single polygon. Okay, so that's the first. Oops, I need something to erase. That's the first action, but we're interested not just on in the graph product, but in its automorphism group. And there's a priori no reason that the automorphism group should act on this complex. And so we'd like to construct a new complex on which the automorphism group itself is going to act. And one intuition to do that is if we compare to the situation happening for mapping class groups or the Higman group, generally you can upgrade an action of the group into an action of the automorphism group when you've got good dynamics. And when I say good dynamics, it's, as usual in this conference, some sort of acylindricity, at least some form of weak acylindricity. You would like that when 2 points of your complex are sufficiently far, you've got only finitely many group elements that fix them pointwise. And in that case, as soon as you've got the local groups GV are going to be, say, infinite, this is far from the case, and this can be seen very easily. So if we try to understand the links of vertices, the links of vertices by construction is quite it's quite easy to see that they're going to be bipartite, complete bipartite, and the reason is the following. We know that so we know that the action is without inversion, so there's exactly n orbits of edges. So I can color every edge by the index I corresponding to by the vertex by the vertex of the graph, such that the stabilizer of that edge is up to conjugation of the form GV. So I'm going to do this. So color each edge of X by the vertex V of gamma, such that stabilizer of that edge E is up to conjugation GV. So now we see that for every vertex, there's going to be the edges incident to that vertex are going to be exactly of two colors, one corresponding to VI here and one corresponding to VI plus 1. And because the relation in the group tells you that two adjacent groups commute, the link of a vertex of X is going to be complete but bipartite, where here these vertices correspond to all the edges of a color, say VI, and here are going to be all the edges of a color VI plus 1. So I should maybe use colors. It's complete bipartite, so now I've got all the... Oops. So what does that? What does having such a structure for the link imply for the action? Well, now it's... We can see that if we take... Oops. Did I lose that long ago? Can you hear me? Or yep. If you take an edge, so you take a vertex in your complex, let's call it, I don't know, U. So you take an edge E with a given color, say red. So you've got other edges E prime of the same color, and you've got another color corresponding to the other possible vertex. So we see that we've got an element of the group sending that edge E to the edge E prime, and because the stabilizer is exactly the direct product of the GV red with the GV yellow, we see that the stabilizer of E is going to be exactly the stabilizer of E prime whenever E and E prime have the same color. But now, what does that mean? It means that if we keep doing that, now looking at the vertex here and keep going that way, we can construct whole subcomplexes which are stabilized by the same subgroup here. So if we construct some subcomplexes which were introduced in the work, for instance, of Bourdon and Pajot, which are called wall trees. So the maximal connected subgraphs of the one skeleton of a given color so what we get is, so we take an edge which is colored with a vertex V. Now you take all the adjacent edges colored with the same V, and you keep doing that. So what you're going to see appearing is gonna be isometrically embedded subtrees, and because each edge has an identical stabilizer, we see that the whole tree, let's call it T, the whole tree T is stabilized by at least stabilized by that the stabilizer of a given edge E. Right. So in particular, as soon which is of the form, as we said, GVI. So as soon as we have a local group in that graph product which is infinite, we see that the action is far from being cylindrical, because we've got huge isometrically embedded subtrees of the complex which are stabilized by an infinite subgroup. So we want to get rid of that, and well, so we're going to do the natural thing to kill those annoying subcomplexes. We're going to construct a new complex. Well, the vertices are exactly those subtrees. So new complex and new action. So now we're gonna construct a complex, as usual, given by vertices, edges, etc. So the vertices are going to correspond to the wall trees, and now you're going to put an edge between two such vertices, so two wall trees, whenever they intersect. All right, so that gives you a graph, and now so in the Davis complex we filled the cubes. Here we're gonna fill the embedded n cycles, where n is the cardinality of the vertex set of gamma. We're looking at the graph product over an n cycle, and that's this n that we're using here. So if, just a remark, if we just look at the one skeleton, so the graph construct by the pattern of intersection of all trees, this can be reinterpreted in a different way. If we go back to the cubical structure on that polygonal complex, this graph is exactly the intersection graph of that square complex, cat0 square complex. So the vertices, where the vertices are the parallelism class of hyperplanes, and you put edges when they cross, not just when the combinatorial, when they are, what's the term? When they touch. It's not the right term, but really when they cross. But in that case, since the links are uniformly bounded, those contact graphs and crossing graphs are quasi-isometric. Okay, so it's the crossing graph here, but with an extra two-dimensional flavor where we've added the cells. So, well, okay, the remark was done. And why do we add those cells? It's to have a much nicer geometry. So you can show, for instance, that as in the case of cat0, proper cat0. All right, the contact graph is going to be a quasi-tree. That was done by Mark Hagen. So the crossing graph in that case as well, since they are quasi-isometric, but adding that two-dimensional geometry is going to make the geometry much nicer. And the first result that we get is that we're going to give it a name, delta x. So that delta x is a small cancellation complex, but more precisely a C prime 1 over 4 T4 complex. So what does that mean? So C prime 1 over 4 is the usual notion. So when you have two cells P and P prime of your complex that intersect, you take gamma a path in their boundary, in the intersection of their boundary. You want the length of gamma to be strictly smaller than 1/4 of the length of P. Well, in that case, all the cells of the same perimeter. So they the intersections of two cells are very small compared with the diameters, with a constant 1 over 4, and T4 means, so that's C prime 1 over 4, and T4 means that the links of vertices have girth at least 4. So you cannot go around a vertex of your complex by going along three polygons. You need at least 4 of them. So something like this. This is okay. So that's the T4 condition, and that's a very nice geometry. So maybe some of you are more familiar with the C prime 1 over 6 condition, which is used, for instance, to cubulate lots of stuff. Turns out that C prime 1 over 4 T4 is also a very nice geometry where you can cubulate many things, and we're going to use that later in this talk. So that was the first thing we wanted. We wanted a nice geometry for a complex, but now we also want a nice dynamics, and the dynamics turns out to be super nice. And I said that the sort of dynamics we wanted was at least a weak form of cylindricity, and we get exactly that. so the action of the graph product on delta x is weakly cylindrical, and more precisely, for two vertices, I'm going to describe the intersection of the stabilizers of those two vertices. So take vertices. So how am I going to denote that? So I'm going to say Vt and Vt prime vertices of delta x with the notation that Vt is the vertex of delta x corresponding to the wall tree T of x. So I'm taking two vertices of delta x corresponding to two wall trees T and T prime of delta x. So if Vt and Vt prime are far apart, but actually just at distance at least 3, then their stabilizer intersect trivially. Maybe I should say that that's the stabilizer for the action on delta x. If their distance exactly 2, then their the intersection of their stabilizer is contained up to conjugation in a group of the form GVI, one of the local groups. If there are distance exactly 1, then their stabilizer intersect exactly up to conjugation in something with the form GVI plus 1. And well, if there are distance 0, so well, let's still do it. So if there are distance 0, I'm just looking at the stabilizer of one vertex in delta x, and the stabilizer in delta x is, so it's just the global stabilizer, not the pointwise stabilizer, the global stabilizer in x of a given wall tree. And one can show that it's a group of the form generated by three consecutive vertices of the graph. So we really understand the stabilizers of pairs of vertices. And why is that very nice? It's really that key fact that allows you to show that not only the group acts on delta x, but the automorphism group as well. And why is that? Because of this proposition, we've got now a completely algebraic description of the stabilizers of vertices and their intersection. So we can completely reconstruct the complex. We can completely reconstruct the complex in purely algebraic terms. So what does that mean? So a corollary of that is that the automorphism group of G acts on delta x. So how does one see that? So from this proposition, we see that the stabilizers of vertices are up to conjugation. Groups of that form. So stabilizers of vertices are up to conjugation. So the form vi minus 1 vi plus 1, which by definition of the graph product is just GVI direct product with GVI minus 1 semi-direct GVI plus 1. So in particular, it's a direct product. And it turns out that those subgroups are exactly the maximal subgroups that split subgroups of G that split as a direct product. That's something that's known for graph products. Whenever you've got a subgroup that that splits as a direct product, it's contained in the subgroup generated by some link, some star in the graph. So in particular, what does that mean? If we're looking at an automorphism group, an automorphism of the graph product, it has to take a maximal subgroup that splits to a maximal product that splits. So in particular, we see already, just from this characterization of stabilizers of vertices, that an automorphism, that the automorphism group of G acts on the vertices of delta x. And now the problem is to see if we can extend this action on the vertex set into an action of the whole complex. But that's going to follow from the characterization of those pair of points. Now, if you take two elements, two vertices vt and vt prime joined by an edge in delta x, so we know that if we take an automorphism phi, so it's going to be sent to a vertex phi of vt and phi of vt prime, and the game now is to show that those two vertices are actually connected by an edge. Right? So what are the possibilities? If those two vertices were at distance at least 3, it would imply that the stabilizer of this vertex and the stabilizer of this vertex intersect trivially. But then, back with the automorphism, it would mean that the stabilizer of that vertex and of that vertex intersect trivially, which is not the case. So we already know that it cannot be at distance at least 3. So the two possibilities are having vertices at distance 1, which is what we want, or 2. So we cannot have distance of phi vt prime at least 3, otherwise, by the proposition, we would have stab of vt intersect stab of vt prime trivial, which is never the case when you look at two crossing wall trees. So they can be at distance 2, which is something we want to rule out, or 1, and we're done. So let's look at the case if we had something like this. Suppose that an automorphism is going to send so the subgroup corresponding to the wall tree T to some wall tree phi of T, and here phi of T prime. And so there are distance 2, which means that they do not intersect, but there's a common wall tree that cross them both. So one can show, one can show using the combinatorial geometry of small concession complex, that actually the stabilizer of the red tree phi of T and the yellow tree phi of T prime has to be contained in the stabilizer in that purple path, between them. So in particular, what does that mean? It means that those stabilizers intersect along something. Yeah, so these stabilizers are contained in a stabilizer of an edge, which is of the form G of Vi. But there's a fundamental difference between something of this form, G of Vi, and intersection of stabilizers at distance 1, which correspond to those subgroups Vi and Vi plus 1, because those, in a graph product, those subgroups are self-normalizing, while these subgroups are never self-normalizing. In particular, you cannot have an automorphism that takes a pair of subgroup whose intersection is self-normalizing to a pair of subgroups whose intersection is not self-normalizing. Right? So you cannot have something corresponding to two vertices at distance 1 send to two vertices at distance 2. So that's really what is used to show that this case cannot happen. So if you have two vertices that were at distance 1, they're going to be sent by an automorphism on two vertices which are again at distance 1. So in particular, you get that the automorphism group really preserves the one skeleton, and then by construction of the whole complex, it's clear that once you preserve the one skeleton, you preserve the whole complex. So you really get in the end that the automorphism group of G acts on delta X. Okay, and what's nice about that is that you can now use dissection to completely understand understand the structure of the automorphism group and to understand a bit of its geometry. So the first thing that we could prove is to completely compute the automorphism group. So the automorphism group of these graph products are isomorphic to a semidirect product of G, seen as the group of inner automorphisms, with well, the rest of the automorphisms are the ones which are in a sense obvious. The first thing you can do is take an automorphism of each of the local groups and put them together. So what you get is the direct product of the aught of automorphism groups of GV, for V a vertex of your graph. And you can also take the symmetries of the graph into account. You've got the automorphism group of your graph gamma, but gamma with a labeling, because in a graph product the gamma every vertex comes with a group attached to it. So you have to preserve the labeling coming from the isomorphism class of GV. So what I mean is, now I see gamma as a labeled graph where each vertex V is labeled by the isomorphism class of the group GV associated to it. So that's the whole automorphism group. So in particular, this part here is the out of my graph product. So in a sense, it's very close to the description you have for rags in that case. Say if you're just looking at a rag, a right-angle arcing group along a long cycle, so at least n vertices. So we know that. So we've got the Lorentz set of generators, but we know that some of them do not happen. And the only automorphism that we get in those cases are the inner automorphisms, which are here. These correspond to the inversions in the RAG, where you're allowed to send a generator to its inverse, and these correspond to the symmetries of the graph, which are also in the generator set of Lorentz. And the last two, the partial conjugations and the transvections do not appear for long cycles, and that's the same here. That small cancellation geometry prevents any sort of automorphisms. So that's the first result, like an algebraic description of the automorphism group. And the second thing we could get was to use more of the geometry of the complex and the geometry of the action to this time understand a bit more about the geometry of the automorphism group. And in particular, decide whether or not this automorphism group presents some sort of non-positive curvature. In particular, whether or not, wrong color. Whether or not these groups of automorphism is asymmetrically hyperbolic. And that's actually going to be the case. There's a small restriction. We're just going to assume that all the GVs are finitely generated. As usual, you're taking the graph product along these long cycles, and then you get that the automorphism group of G is asymmetrically hyperbolic. So we've seen the definition many times. So it's a form of admitting hyperbolic-like features for your group. So how does one prove that? So we're going to use the geometry of the action on a small cancellation complex. So as we've seen in previous talks, to show that a group is asymmetrically hyperbolic, you have to, like, the ideal case is when you can find a group element which is going to be WPD and strongly contracting. So strongly contracting is not going to be a problem because the space we're acting on is hyperbolic. But showing the WPD condition is, as usual, something really painful because you have to deal with coarse stabilizers, so there are lots of constants involved. But in order to avoid this problem, we're going to use a criterion which we obtained very recently with Indira Chatterjee in the case of actions on cat-zero cube complexes. And the way to pass from the world of small cancellation complexes to the world of cat-zero cube complexes is to use the work of Wise. So we know that by the work of Wise plus some minor things, we can send delta x, our small cancellation complex, into a cat-zero cube complex C of delta x, such that we have a quasi-isometry here, and which is equivariant. So we've got the action of out of G. We're going to have the action of our group here as well. So basically, to show something like to show like all the WPD conditions and that sort of things here, we just have to consider an action on something which is like well behaved, such as actions on cat-zero cube complexes. And so with Indira Chatterjee, we obtain a very nice and very useful criterion to show that a group is asymmetrically hyperbolic, which is the following, which is extremely simple to check, and so quite powerful. So suppose that we've got a group, so G is already taken. What could I take? H acting on a space, on a cat0 cube complex Y, which is so CCC, finite dimensional, and the action is as well. It's a Capra-Sergeyev action, so essential and no fixed point at infinity. And so suppose that in that cat0 cube complex you can find two hyperplanes, H1 and H2, and I forgot something, finite dimensional, irreducible. You can find two hyperplanes H1 and H2 such that their stabilizers intersect along a finite subgroup. Then automatically H is either virtually cyclic, or cylindrically hyperbolic. So it's something which is very easy to check. You just have to find two hyperplanes and understand the way their stabilizers intersect. So that's something that can be used to recover the asymmetrical hyperbolicity of many classes of groups. It can be for the Higman group, it can be for some subgroups of the three-dimensional Cremona group, which I studied earlier. We used it with Indira to show the asymmetrical hyperbolicity of some Artin groups of type FC, and it can also be used in that situation, because in that duality between or not duality, but that association of a cat0 cube complex to a small cancellation complex, the hyperplanes essentially correspond to the walls of the initial complex. So understanding the way the stabilizers of hyperplanes intersect is essentially understanding the way the stabilizers of walls intersect. And now we can use the very nice small cancellation geometry of the complex to find walls that are gonna satisfy this property. So that's the two main results that we obtained. On the one hand, a complete algebraic description of the automorphism group, and on the other hand, some nice understanding of hyperbolic features of this automorphism group. So of course, the ideal case would be not only for long cycles, but for graphs which have a very for a large girth. But yeah, there's more work to be done to generalize the arguments here. So I think I'm going to stop here. Thank you.
Any questions? So you talked about generalizing the graph. I mean, how about so from one point of view, you're studying groups which are acting on right-angled buildings, right? So how about generalizing to other buildings? I mean, it seems to me you're only using the building structure, right? So that seems possible.
That's well, but we also something quite important also is the fact that the links of vertices are really complete bipartite, which is like essentially like being right angle.
Yeah.
So I don't know if you might want to do something similar for more general types of buildings. Which I mean, it's not clear to me that the same sort of geometry would be there. It's possible.
Let them speak again.